Oh, one second.
Which further ado.
Without further ado, Todd Trimble on the universal properties of the bar construction.
It's very nice to be back. This is my second time here. And yeah, thanks for having me. So let me see about this. Yeah, I was going to spend about 5 or 10 minutes explaining where some of this stuff comes from. Just by way of background, I met Raymond and Gershom at the Category Theory Oktoberfest, and I think they reported that they had seen some scribblings of mine on the bar construction, and they asked a few questions about that, which I thought it would be nice to follow up on. I think I recall, too, that last time we were speaking briefly about the Tamari lattice. Is that correct? Mm-hmm. And I made an offhand observation that this could also be seen from the perspective of the bar construction. And so, yeah, this will be an introduction, hopefully very accessible, down to earth. Nothing too fancy, except possibly at the beginning. Now, this is kind of awkward. I want to show my face at the same time that I'm flipping through, so we'll see how this works out.
Okay.
Okay. So, what are bar constructions good for? They come up a lot anytime you are in need of an algebraic structure which is either contractible or is acyclic. Then a bar construction is your friend. It will give you, it will allow you to freely generate a suitable algebraic acyclic structure. That's what they're good for. So, let me give some examples of this. It's a long and storied history where these things come up. From my point of view, just again by way of background, my thesis advisor was Miles Tierney. He was an algebraic topologist, and so I have some sort of, this feels very much close to my heart, the topic of classifying bundles, which I don't know how many people here in this audience are okay with classifying bundles, but historically this was one place where these acyclic constructions first came up. So I'll just say very briefly, you have a notion of a G bundle, and so what that means is you have a space E over a given space B, and E is equipped with a G action for some topological group G, and that G action should be fiber-wise, so it should take elements in a fiber to elements in the same fiber. And there's a local triviality condition for G bundles. I don't think I'm going to talk about that too much. But the point is that these come up all over the place in algebraic topology. Classic example would be K-theory, where you're looking at complex vector bundles and a suitable notion of stability for those. And the idea is that there's a classifying bundle for any topological group. So if you have a G bundle, there is a very specific universal G bundle, E mapping down to B, so that if you're given another nice space X in a G bundle over X, then there exists a map, which I'm calling chi here, mapping into the base space of this universal bundle, which is unique up to homotopy, and such that when you pull back the universal bundle along this map chi, you get the given G bundle over X up to isomorphism. So the classifying constructions are just ubiquitous throughout mathematics, and this is a primary case of that. This theorem that for any topological group G does have a classifying bundle, that was proved by Milner quite some time ago, I think in the 50s or something. But the crucial thing that you need to get this thing to work is, to make it tick, is that you need for the total space of the universal bundle to be contractible. That's the acyclicity condition. That's the key thing that you need in order to be assured that you have this universal bundle. It just works out beautifully like that. But that's what you want to construct. Milner gave a nice construction of this, and some years later, Milgram gave another construction which fits into the theme of my talk, where he gave what is in essence a bar construction to make this contractible space on which G acts. Another place, this is even more ancient, it comes up in homological algebra. So you may remember that one is often interested in, say, group cohomology, in which you are looking at G modules A. It's sort of the same situation as before, except that now A is an abelian group and G acts on it. And one wants to construct group cohomology. I'm not going to get into a lot of details about that, but in a nutshell, what one does is takes a trivial module, let's say the integer is Z with a trivial G action, and one tries to construct a projective resolution or a free resolution of that given, I'm calling it A here, but it's typically a trivial module. So you construct a long exact sequence, or at least it's exact everywhere except for the first spot where the homology should be A. That will be a resolution of A is what we call it, or I'm calling it an acyclic resolution. A free acyclic resolution. So then one sets up group cohomology by taking this chain complex and then homming into some other object B and taking the cohomology of that, and that defines group cohomology. But the basic point is that we need acyclic resolutions, and I mean, you can kind of construct them in silly ad hoc ways, but this subject being due to Eilenberg and MacLean, they came up with the original bar construction, which we're going to get into a little bit later, but this gives you a very uniform method for actually constructing these free resolutions. And the thing I want to emphasize here is that this is not just on the chain complex level, but this is inherently a simplicial construction. So that will come into play. Just very briefly, I mean, I mentioned up here that these X functors are used to construct group cohomology, Lie algebra cohomology, other things. For a great many monads, there's something called monadic cohomology. And the idea is that we're working with monads here. This is working with a very pure categorical concept. And the junctions which are classically associated with these monads, we're going to see that these give rise to simplicial objects, and that will be sort of the main character of our story.
Well, was that first done by Beck and Barr?
Barr and Beck are prominent names, yeah, in the introduction of what they call triple cohomology. Triple being another word for monad, but yeah. Now we come to Stasheff. We were just talking about him a few minutes ago. In the context of the general study of classifying bundles, these are intimately related to deloopings of spaces. So, I mean, one way of thinking about the construction given by Milgram or Milner is that it furnishes you with a delooping of a topological group, meaning that it produces a base space, which I called B before, whose loop space is homotopy equivalent to the given group G. Stasheff studied this in a great deal more generality. He more or less pinned down the conditions that you need for a Hopf space, an H space, to admit a delooping. And so for that purpose, he introduced what are called associahedra. I'm bringing that in because I mentioned associahedra as possible application. In essence, he did use a bar construction to construct the appropriate universal bundle for a K-algebra. How many people are familiar with these associahedra? Well, okay, good, excellent.
I know what they look like in pictures. I think of them as an operaad of a loop space or whatever. That's not apparent to me.
Yeah, so I mean, K here is what is called the topological operaad, and you can define algebras of the operaad where you interpret the points of the operaad as being operations on a space, and that's sort of the gist of that. So yeah, but I was going to say that actually the associahedral operaad, I guess, was the first operaad historically speaking. And it can be constructed by means of a bar construction. So we can set up, I may get to it at the end, but we can set up a monad, which we can call the free operad monad, and actually construct the associahedra, or their barycentric subdivisions, by means of a bar construction. And if you've seen Stashev's papers, he also speaks about not just A-infinity spaces, which are the same as K-algebras, but he talks about A-infinity maps. The description of the maps gets pretty complicated, but the cellular shapes, if I can put it that way, are captured by what are called these multiplahedra, and those two also admit a kind of bar construction description.
What about a permutahedra? Because those aren't free in some sense.
Yeah, I'd love to be able to answer. Let's see. Yeah, I mean, so those are intimately connected with, I suppose, symmetric monoidal categories and actual permutative operads. Can't really say that they can come up with from a bar construction that I'm aware of right now. I want to put a pin through all these questions, because, yeah. Yeah, well, I mean, as long as we're talking about associahedra, I mean, if you've looked a little bit into higher category theory, you will see things like bicategories, which involve the famous Stashev pentagon. You will see tricategories by Street, Gordon, Power, and Street. And if you look at these cellular shapes of the structural constraints that come up in these higher order categories, they look just like associahedra. Or the maps that you need, like homomorphisms of bicategories, they partake of the cellular shapes of multiplahedra. So my feeling has been for decades that bar constructions ought to be useful for delving into the combinatorics of higher category theory.
And I know you're being humble by not mentioning the tetracategories.
It's almost an embarrassment about the tetracategories. There's John Baez put up on his website my official 40-page definition of tetracategory, and involving the huge, massive diagrams based on K6 is what it is actually. I got a lot of ribbing about that over the years, and people. I think the general feeling is that this is combinatorially too complicated to go down that path. I don't know. I hold out hope that we'll come back to that sometime or other. Let's see. Yeah, and as far as deloopings go, I mean, may use two-sided bar constructions, which I might like to talk about sometime in the future, to construct iterated deloopings. So anyway, I'm making a little sales pitch that bar constructions just come up all over the place. But really, the nice thing is that bar constructions are pure category theory. It's just pure categorical algebra. No fuss, no muss. There's no topology necessarily. It's just beautiful, just equational categorical logic. That's what it is. Before I get into the actual bar construction, I need to tell you a little bit about what I call the generic monoid. I think maybe some of you can anticipate where I'm going with this, but I mean, we're going to talk about simplicial sets. So I'm going to have a setup for us in which simplicial objects will arise very naturally by considering what you might mean by a generic monoid. So let's talk a little bit more generally about generic algebras. I'm using a fancy term here, inside doctrinal environments. So just to give the classical example of this, if you wanted to define a group object in a category, what do you need? I mean, what do you need to define a group object? You need Cartesian products. Okay? And then you could define a group object. And there, that would be an object equipped with a suitable multiplication, an identity element or an identity map from the terminal, and an inversion operation satisfying the usual equations that you expect for groups. One thing to point out about this is that groups actually partake of all the structure of a category with finite products. In that, when you try to write down the equation that generalizes one of the group axioms, it says that x times x inverse is E, then you'll notice that on the left-hand side of that equation, I have to duplicate a variable. So I need to have it twice. On the right-hand side, I don't have it at all. In order to encode that, to encode the duplication, you apply a diagonal map, which will take x, an element x, and duplicate it, and then you can go ahead and apply the operations. So you're going to have a commutative diagram. For the E on the other side, there's a unique map to the terminal, and you follow it by the unit element, and you make a nice commutative diagram about that. And that's how you define a group object.
Just before, what do you mean by doctrinal environments?
So, yeah, doctrine is... there's some controversy about what... No. There's some controversy about what you mean by a doctrine, but I generally have in mind something like a theory of structured categories. So, categories with finite products, monoidal categories, symmetric monoidal categories, braided monoidal categories, all these categories with finite limits, all these give you.
This won't work in a monoidal category structure.
This will not work in a monoidal category structure because of that equation.
Because of the diagonal.
That is the point, yes. That is a point. So if I were to go on and talk about what is meant by the generic group, well, I think I sort of stepped ahead of myself. There's a certain mystique, perhaps, amongst mathematicians about these Lavier theories, and what are they? What is a Lavier theory? There are various explanations that are given. Lavier used Lavier theories as a nice categorical way to do universal algebra. But if I had to tell you what is the Lavier theory for the theory of groups, I would simply say this: it's the generic group. So the idea is that you imagine a scenario where you're trying to construct a generic group, so you need a category with finite products, you need a group object, and that's all you assume. So if it has finite product, you have a group object with underlying object G. With finite products, you can take G squared, G cubed, and so on. And so those are all the objects. You have nothing more. And the morphisms you form just by putting together the group operations and taking their Cartesian products, crossing them or composing them. So just imagine that the universe of all operations that you could build up from finite products and the group operations, and that is the Lavier theory.
Right, and only assume the relations and the axioms of the group.
That's right. You don't assume any more axioms than what the group axioms give you. That's it. And the idea is that if you have a generic group, then you can interpret, by means of a finite product preserving functor, that generic group inside any other category with finite products, and you get something tantamount to the notion of group, the category of group objects in that category. So this is a nice universal way of saying what you mean by that. Lavier theory. Yes, to define a monoid object, you need less. So we don't have this business with inverses and the equation that has to satisfy. You don't need categories with finite products with all of its accompanying diagonal maps or projection maps down to the terminal, what have you. You don't need all that. Just all you need is a monoidal category, which for my purposes, just for convenience sake, let's assume that our monoidal categories are strict. The monoidal unit will be indicated by I, and the monoidal product by its tensor product. And again, yes, you have a notion of a monoid object and the equation, the associativity and identity equations that it must satisfy. And you might, if you don't already know the answer, you might think to yourself, what would be the generic object, the generic monoid? So that would be a monoidal category with a monoid object and assume nothing more than that. So I want to play around with that a little bit. If you haven't seen it, then it's kind of fun. I'm going to use the method of string diagrams to give an idea of what to expect. So with string diagrams, the idea is that you exhibit on a planar surface objects and morphisms of a monoidal category by means of edges and nodes. And the idea will be that when you want, so this will be an example. If you want to refer to, for example, a morphism from one monoidal product to another, then what you do is think of the tensor product as being exhibited by simple juxtaposition. Objects will be represented by edges, which are labeled as the appropriate objects. Morphisms themselves will be indicated by nodes. So the idea is that we're going to represent or depict the morphism by a diagram that looks like this. And then you have a means of tensoring. Tensoring will be indicated just by juxtaposition. Composition will be concatenation. So you can, something like that, right? So the idea is, so we start off with a monoid object in a monoidal category, and we try to build up the general sorts of diagrams subject to the associativity, subject to unit equations. So the single object M for the underlying object of the monoid is just represented by this. The multiplication would be indicated by a string diagram that would look like this. I should mention string diagrams are a perfectly rigorous calculus developed by Joyal and Street for performing these manipulations and calculations in monoidal categories. So there would be the multiplication. If you want to refer to the associativity axiom, then you can kind of concatenate. So this bit above the vertical line would be M tensor identity map on the monoid, and then so this will be representing M composed with M tensor 1. And so the idea is that now you're imposing an equation for a monoid, and you should get that this will impose an equation between these string diagrams. And you can juxtapose them and so on and so forth. There's a general associativity law that you are familiar with from algebra that says that any two morphisms going to M of the same arity, meaning M to the n, M to tensor power n, have to be equal. So that's going to mean that if you're referring, for example, to morphisms of arity 3, well, they're all the same. Why not just identify them all with a single thing that looks like that? So now we see what we're getting here. I mean, now if we're talking about a general morphism, you can see. We're talking about a general morphism now from, say, M to the M, M to the N. Then, I mean, you're basically talking about something that looks like this. You have a unit, of course. I didn't mention the unit. That's you have 0 strings coming in, so the unit might be represented by something that looks like that. Yep. What do we have? What we have is, if you stare at this a moment, we have an order-preserving map between two finite ordinals. So you can just, label these things 1, 2, 3, 4, 5 like this. Here's 1, 2, 3. Here we have exhibited an order-preserving map between two finite ordinals. And so I would say that it's the simplex category. Simplex category is the category of finite ordinals. I should actually, let me get into view here. Actually, I'm referring to what is called the augmented simplex category. So I am including 0, the empty ordinal, as being one of my objects. Okay. So when I say simplex category, for the sake of this talk, I'm referring really to the augmented simplex category.
If you were to talk about the unaugmented, you would be talking
remove the empty ordinal.
Instead of talking about monoids, you talk about semi.
You could. You could. It's not as clean. I mean, I don't know. I think monoids are much nicer, generally speaking. You have a unata lemma. If you remove identities, there's no unata lemma, for example. So. Yeah. So the monoidal object is simply the one element ordinal, 1. The monoidal unit is 0. And we again get something analogous to the statement before about the Lavier theory of groups. The category of monoidal functors, let's say strict monoidal functors, from delta, this augmented simplex category, into a straight monoidal category, is equivalent to the category of monoids in that straight monoidal category.
If you went to Lavier theories of monoids, and you talked about products, then you'd have monoidal objects in the category of...
Indeed. Yeah.
And so how is a monoidal category, a monoidal object in a category different than monoids in C? It's just the tensor product? You're not assuming that there's a...
It has to preserve the monoidal structure.
But you're assuming C has a monoidal structure, not a
I'm assuming C has a monoidal structure here. So.
Not a Cartesian
Yes,
product.
That's right.
And the map has to preserve it, which it doesn't in the case of the co-simplicial object.
There's a little piece of yoga here that another way of defining a Lavier theory is you look at the finitely generated free algebras and take the opposite category. And that gives you the Lavier theory. I like the other way of describing this more concrete, more down to earth.
Is there a generalization of that for delta? In other words, is there some way of reconstructing delta as the free something of something?
Well, I thought I just...
No, you just defined the
that
Lavier theory
that would be
of
delta
monoids.
enriched with finite products.
Not the Lavier theory of... so I'm a little confused. I'm working with it, here I'm working in the doctrine of just monoidal categories.
Right.
So I'm not talking about Lavier theories at the moment.
Oh, okay.
I wanted to give an example of how this gets used. So yes, so we are saying that monoidal functors from delta into a monoidal category are essentially equivalent to monoids in the monoidal category. So I'm going to take an example of a monoidal category, a semi-exotic example. We're going to look at the category of topological spaces, and our monoidal product will be what is called the join of two spaces. What that is you let's just imagine that you have two topological spaces, and you embed them in a very high-dimensional Euclidean space, and then imagine the space of all line segments that actually connect those two spaces. That's the intuitive idea. This is the formal categorical description of the monoidal product. So I here is the unit interval from 0 to 1. If you were to take X, for example, to be the empty space, then virtually all of that diagram would just vanish into thin air, except for that little Y that's sort of hanging at the tail, and therefore the empty space would play the role of the monoidal unit. If, on the other hand, X and Y are not empty, then pretty much the description I just gave in terms of putting spaces in generic position and looking at their line segments, you can say it a little bit more formally by describing the points of X join Y as being triples X comma T comma Y, where T is a parameter between 0 and 1. And you can think of the points as being formal convex combinations of the points coming from X and Y. Subject to, if you're actually at a tail end, then you're definitely identified with that tail end X no matter what Y is. And same for Y. If you looked at a triple monoidal product, then you could think of the points in that as being convex combinations of 3 points. So here, S, T, and U are numbers between 0 and 1, and they have to add up to 1. That's what you mean by convex combination. Okay, that's monoidal category. Inside this monoidal category, we have a terminal object. That's just a one-element space. Nice little fact about the terminal is it's always a monoid. Whenever you have a monoidal category with a terminal, that's always a monoid. There's only one way to define the monoid structure.
Sure.
So that gives you a monoid. Therefore, there is an induced monoidal functor from delta into topological spaces. It would take an infold tensor product of copies of this terminal, that's in here, to an infold join of ones. And if you count the number of parameters here, this is an n-1 dimensional simplex. So we have actually defined the simplex functor in this very slick way. I mean, it's terribly slick. Of course, you have to verify that you actually do have a monoidal product. But, brushing that under the carpet.
So that generally sort of realizes the simplices as actual frickin' triangles.
Exactly.
Right, so you've constructed geometric realization categorically.
Yeah. Yep.
Very slick.
Yeah. Yeah, so that's one little application. And now I want to get to the actual bar construction. It's very simple. For a category theorist, it's very simple. So, we can keep playing this game. If you were to take the opposite category, the augmented simplex category, then that would be the generic comonoid. Think of that as describable by these types of string diagrams on the board, but except you turn them upside down. We're in fact going to do that in a little while. Now, let's say we have a category E, and we have a monad on E. Everybody's familiar with the notion of monad. Everybody here is familiar with the notion of a T algebra for a monad T. And this is called also the Eilenberg-Moore category, and there is a famous adjunction taking place between the category of algebras and the underlying category E. We have a free functor going from E to the category of algebras, left adjoint to the underlying functor. I use U for underline. And if you are very comfortable with category theory, then you know that you have a unit and a co-unit for this adjunction, satisfying famous triangular equations. All that will come into play. So, we're not going to be looking at the monad per se. We're going to be looking at the comonad that you actually have on the category of algebras. So the comonad will be, well, I'll call it FUs. That means you first go from the algebra category to E, and then back to the algebra category by applying F. I want to call that comonad K. That has a co-unit, which I'm indicating by epsilon. And there's a co-multiplication, which is generated by the adjunction data. Just to make sure that we're all very definitely on the same page, let me remind you about the nature of the co-unit for the algebras. So the co-unit you should think of as being the unique algebra map that you would, how do you put this? So let's take, for example, free groups. So you would have for any group G, the free group on the underlying set of G, and you can interpret this as being words in the elements of G, subject to appropriate equations, and then you have a map, which I'm calling epsilon, which interprets that word by taking their product inside of G. So that's just a brief description of what co-units are like. Yeah, I think I skipped over something. A comonad is a comonoid in an endofunctor category. That's a very nice, slick way of describing comonads. Therefore, you guessed it, we're going to get a monoidal functor from delta up now into the endofunctor category, which I'm indicating with this square bracket notation. So it would take in, which of course is an infold product inside of delta, to the infold endofunctor composition of FU. Now we define the bar construction. So if you're given a T algebra, just one in particular, you can do something very simple. You can apply to this what we call this is a simplicial T endofunctor. You can evaluate those endofunctors at the given algebra object. That's indicated by this evaluation functor here. And to bring us back to the intuitive description I gave of the bar construction, we're going to think of that intuitively as being a so-called T-free acyclic resolution, which I'm going to explain all this stuff. But that is how one thinks of this bar construction.
So there's a notion of acyclic that work in this high level of generality.
That's right, that's right. There's a notion of acyclic for simplicial objects for any category E.
Can we unpack a few words here?
Yeah.
So you've written a formula for the bar construction, and you said this formula is the formula of a, quote, simplicial T algebra.
That's right.
And I'm trying to put those words together. So A is a T algebra, right? And you said, and so what is it, the type of a T algebra? It's I'm just trying to think this through. Like it's an evalomorphism, right? Basically, is a T algebra, right?
Well, so a T algebra is an object of E equipped with a map, called the object A, equipped with a map from TA to A, which satisfies some associativity and union conditions.
And so what's the T algebra here? We have an object of what equipped with a map? We have now an object of, because we have ET.
It's a simplicial T algebra, which means it's a simplicial object whose
values, let's say.
No. Bar of A is a simplicial algebra. A is just
well,
a T algebra.
A is just a T algebra. That's right. And then we form this guy up here, which is an endofunctor,
T algebras,
and apply it to A.
Sorry. Let me try once more, and then.
I think it would be good to write down the definition. A T algebra is T of A going to A.
Let's do that.
Yeah.
Let's go over it because I'll erase those.
I would think simplicial T algebra just was something that was delta op to, you know, an object that was T algebra. So for each delta op.
So T is a monoid on E.
Yeah.
T is a comonoid on E.
So A is an object of E, and this is equipped with a structure map, I'll call it alpha, from TA to A. And there are two conditions that need to be satisfied. So here's the action, and the action, here's T applied to the action, and this is the multiplication on the monoid evaluated at the component A. This diagram must commute.
Right.
And the other diagram that has to commute is you have a unit for the monad, which are called U, so you take the component of U at A, get a map into TA, follow it by the action, and you should get the identity map on.
So then the question is, then you stick the word simplicial in front of the phrase T algebra.
Yeah.
And you've given us a formula for a particular simplicial T algebra. What is the general sort of...
All the simplicial object means is a functor from delta op into the given.
That's what I'm saying. So we can think of everything after the delta op arrow as fitting in, as being a T algebra in that sense. That's what I'm trying to That's why I'm trying to... You see my problem there.
Now you've got natural.
These are not T algebras. These
When
are
you compose
That's what I was trying to
composite will
You
go
see my
down the
confusion.
end.
It's terminologically, I think that if you say simplicial X, then I should just see delta op arrow and then...
Well, you do. You just have to compose two arrows here.
Okay.
Yeah.
Oh, maybe that wasn't clear.
Simplicial is.
Maybe that wasn't clear. Often when I put
Actually,
things
it's
inside of
right.
parentheses, I mean to compose those two arrows to get a single arrow
Yeah.
now
Okay.
from delta op into the category of algebras.
Okay.
And, okay, so now let's bring it a little bit more down to earth. So we defined the bar construction. I tell you what it does at an ordinal, but I mean there's a straightforward description which follows from the above. So these are, when you're writing out simplicial objects, if you've ever worked with them, then you'll see these components, and you have faces and degeneracies, but these are the objects. And when it
So I
comes
guess in particular, inside the parentheses, the first arrow is the same as the arrow above. Just doesn't have a label.
that's right.
The second one's evaluate. The first one is not any old arrow. It's that specific one on top of the slide.
Right.
Right, yeah.
Okay.
Well, I see, yeah, never mind, I was, yeah, I got it. I got it.
Okay, so as I say, if you've ever worked with simplicial objects, then, I mean, what is traditional is to describe the face maps and the degeneracy maps. I've never remembered how the simplicial identities go. I mean, I would have to reconstruct it every single time. What I do is I use string diagrams if I'm in this context to keep track of what needs to be said. So, I mean, the idea is that you have face maps going from in to n minus 1, and basically, we're in delta op. You have to be a little bit careful about what you're doing here. But let me give you an example of a face map from 3 to 2. So remember that in delta op we're turning things upside down. This is the upside down unit. And this would be an example of a face map where you're going from 3 to 2 here. Right. So that would be one face map, and here's make it even simpler, going from 2 to 1 inside delta op. So there's one, and the other one would look like this. And now let's just try to think about, how that would manifest. So, right, I mean, what is the comonoid here? The comonoid is what we called FU. So let's expand this a little bit. Here's one face map, but to expand it out a little bit more, what's happening is that this is what I'm calling K equals FU. Here's another copy of K inside the endofunctor category. And then you have A here. Right, so the way you can display this is that K being FU, there's going to be a co-unit here. So think of this as being an expanded version of the actual co-unit. Followed by, here's FU. And here comes A along for the ride. You can suppress A if you want. It works inside the endofunctor category. Okay, so this will be one face map. What's the other face map corresponding to this? The other face map would look like, well, here's FU. This is K again. And yeah. Yeah. So this is what I want to indicate here. So this will be the other face map. So here's one face map. Here's the other face map. We're working with augmented simplicial sets, so you have also one, and this is the augmentation component down here, which for topologists is usually missing, but if you're talking about ordinary simplicial objects. But you have, so you have all these face operators which you can generate by using the co-unit. If I'm looking at a triple K to double K, you have 3 face maps, and you would have epsilon KKA for the first, K epsilon Ka for the second. You just kind of slide the epsilon along down the path. and generate 3 of them that way. Oops, oh shoot. So I wanted to give an example and keep it pretty down to earth about how this is working. Let's actually work out what the nature of the classifying bundle was that I started off this talk off with. So we're going to start off with a monad on top. That monad will be G cross blank, where G is a topological group. So you're going to get a monad structure which is induced from the group structure. And for each algebra, so you defined as before, the unit and the co-unit for the adjunction that you get here. The unit here, if you have a space on which G operates, then this co-unit would take the pair G comma A just to G times A with respect to that action. And the unit looks like this. Now we're going to apply that to the particular algebra A, which is going to be the terminal space. And I just want to spend a moment milking out what the actual bar construction looks like. So yeah, we have, this is just at the face map level, but we have these maps, where epsilon will appear in certain positions. Epsilon 1, well, that's just a unique map to 1. I indicate that by the unique map. Let's look at this, G cross G to G. The first one, the first face map, will take a pair G1, comma G2, and G operates on G cross 1 just by multiplying the leftmost component. So the first face map, which I'm going to indicate by D1, we'll just go to G1, G2. The second one, G1, G2, well, now you have to let G2, that's epsilon of the second component, you have to let that act on 1, but it more or less disappears from view. So you're just going to get that. Those would be the two face maps in this case. And then you have 3 face maps. Yep. By the way, this is where the terminology bar construction comes from. This is due to Eilenberg and McLean. Instead of using commas to distinguish these elements here, like in a triple product, they use bars. And the effect is that the first face operator will simply remove a bar and multiply inside the group. And the second one will remove the second bar. And in the third one, well, you just kind of push the last one off the cliff. And so I don't know how much time I want to spend. I was going to draw a picture of a 2 simplex inside this and what it would look like. Maybe I'll skip that. And then what one does, now that you have the bar construction for this terminal object, you've got this, this simplicial G space, which I've indicated on the last slide. And then you apply what's called geometric realization. There's a sort of fancy mechanism for describing it in terms of a coend, but that's the description. The sigma here, remember, that's the simplex functor that we defined before. So.
Yep. You already gave that, assuming you've constructed the reals earlier with your join, right, or not?
Well, he did it for one simplex, but now he needs to do it for the whole complex, not just one simplex.
Okay.
Now, yes,
But
use the coend to join them
It is
together.
dependent upon taking that T seriously as being realized as a real between 0 and 1, with some relation.
Oh, T meaning little t being the
little
parameter.
T, yeah.
Mm-hmm.
This is dependent upon that construction.
Oh, very definitely.
Okay.
Yes, this is not pure category theory at this point.
Right.
I am bringing in
Of course,
topology at this point.
There's a huge effort now being made to do formal things, as in homotopy type theory, where you try to avoid, at least explicitly, you may recover it in some cases, constructing the reals between 0
I'm
and
doing
1.
things very classically.
Right, understood. No, I just wanted to make sure. Okay.
Yeah.
Thanks.
Yeah. Yeah, so the point is, I mean, the whole point of the bar construction is you're producing, in this case, a contractible space. This will be the total space of the classifying bundle. It will be contractible. But why? I mean, it's not at all clear at this point in the story why this geometric realization would be contractible. Not at all clear. but we will, so we want to try to tease that out. So what we are in fact going to do, I'm going to make a claim that there is a notion of contractible or acyclic object. For simplicial objects in any category, there's a notion of contractibility or acyclicity, and that's what we're going to be looking at, with the proviso that we're not looking at the bar construction exactly, but we're going to be taking the underlying functor and sending us back down into the underlying category we started with. So that, I sometimes call it the bar resolution, but that triple composite there is going to be the simplicial object, which I'll turn to be contractible. To talk about the contractibility, I need to say a little bit more on the other side of things. I mean, these simplicial objects also have what's so-called degeneracy maps. That uses the other datum of a comonad, which is the comultiplication. I'm denoting comultiplication by delta here. You might remember that delta, maybe I'll just remind you that delta comes from the adjunction data.
Todd, do you mind if I stop for a second?
Okay, so we're hoping that the battery holds good for the remainder. So I was going to lead us into why we actually get acyclic constructions. For that, I should begin talking a little bit about the degeneracies that are inherent to the simplicial object too. So just to remind you, I mean, all the simplicial structure comes out of the adjunction data, which generates a co-unit and a co-multiplication, which I've reminded you of over here, and it's a co-multiplication which is used to define the degeneracy maps. So I'll describe them here. And again, you have the idea that delta can kind of be pushed along further into the arguments to describe all the degeneracies. So yeah, in longhand, K is FU, and I've just written out more explicitly what these degeneracies look like in terms of the adjunction data. But if we apply U one more time, you'll remember that we started with the bar construction, and then we applied U to get us back into the underlying category E, giving us a simplicial object in E. So if we apply U one more time, I am saying that there is actually room for one more degeneracy. I'm putting it in quotes here. But that would, again, be applying the unit so that the unit would take us from UA to monad at UA, and so on down the line. And that is what we're going to be using. This will play the role of a contracting homotopy, this extra degeneracy that you have available. It's really quite nice. We don't call it a degeneracy. We're going to call it a contracting homotopy or something like that. I can't think of a really good name for it, actually. But some people call it contraction data, I think. At any rate, whatever it is, it's an extra structure on the simplicial object, which I formed here, and which I provisionally call the bar resolution of the algebra. In the description of my talk, I referred to what is called in the business decalage. I don't speak French, so I hope my pronunciation is not too abysmal. But basically what's going to happen here is that this extra degeneracy will be a coalgebra structure for a comonad called decalage. And it's something that you can define on any category of simplicial objects. What it is, roughly speaking, decalage means to shift. The idea is you're going to kind of shift things to the right, just like we saw the sort of the epsilons and the deltas behind the argument. So everything's going to get shifted over by one, if I can put it that way. So what is decalage? So here's how it works. Very simple. You start off with delta up. That has a generic comonoid sitting inside it, which we're calling 1. Anytime you have a monoidal category with, let's say, a monoid, that monoid will induce a monad in the same way that an ordinary monoid in sets induces a monad. M induces M cross blank. the comonad does the same thing. So you start with a comonoid like 1 here, and then you apply it to extra arguments. That, in essence, everything that appears here is being shifted to the right by 1. You stick a little 1 in front of it. So that's the decalage. This is a comonad. So the comonoid structure that you have available on 1, that's sort of flipping the unit upside down in terms of string diagrams, that gives you the co-unit, and that gives you the co-unit for the comonad itself. You just unit op plus blank. And same thing for the co-multiplication on, I'm calling D for, you have a simplex with 3 vertices, that's a 2-dimensional affine simplex. And you're looking at continuous maps from that into X. So imagine here's X, and then you have this kind of shape of a triangle. It's some kind of continuous map from that triangle into X. And that would be an example. Right, so now let's think about this for a minute. So suppose you take n equals 2 here, that would be x of 3. That's a continuous map from a 2 simplex, but we're thinking of that as being a simplicial set at this decalage. So we're going to be thinking of it as a path in the decalage construction. So if n equals 2, you're talking about one-dimensional simplices. And a path in the decalage would then correspond to a map from the 2 simplex into X. So the path here inside of P of X kind of spans out a parametrized set of paths in the original space X, but they're nailed down to a particular point. Okay. So I call it P of X because this is a kind of path space construction. If you'll indulge me a little bit more, you can describe it more or less like this. I mean, in this example for this simplicial set, you can say something like P of X, well, P of the singularization. Well, we're going to be thinking of it as a path space. So it'll be the sum over all points of the space of paths which sort of start at X. Here's X right here. Start at X at time t equals 0. And look at all paths emanating out from that point. So I'm claiming that the bar resolution, that's U applied to the bar construction at the algebra A, and now, well, let's describe what the decalage is doing. What it's doing is, well, maybe I can say it this way. So it's a simplicial object. So this is going to be, now you're going to shift by 1, so you're going to get U bar T A at N. And what is this? Sorry. 1 plus N. So when you're writing all this out, you're going to get U, and then N plus 1 of these things. Okay? As opposed to this, which just had N. The coalgebra structures would be a map from here to here, and that's going to be given by the unit. That's what I'm saying over here. So it's the unit applied to k to the n of A, where k is the comonad. And I'm indicating here very briefly why we're actually getting a coalgebra. So you have to verify commutativity of 2 diagrams. This is the so-called co-associativity But when you write things out, you find that the co-associativity amounts to a naturality diagram for you. Is your cell thing for you?
And then we're going back to the other one.
Okay. Oh, this is too bad.
No,
maybe I should stop. And I hope I'm not
No. We
confusing
have 5 more
people.
minutes, and then you should stop. Well, you know what? Maybe. I'm sorry.
I think the filming is a lost cause here.
Yeah.
No. So do me a favor. I'm sorry about this. Tell me when the last 5 minutes, and then we'll capture that.
Yeah. Okay. I've got a little bit further to go.
Oh, you're doing it.
Yes.
Oh, sorry. Go. He's doing it.
Oh, all right. Perfect.
I'm sorry.
All right.
So you'll
I've gotten 2.5 minutes before this, too.
So the co-associativity comes down to a naturality condition for the unit. And the co-unit, that equation that you would need for a coalgebra, that's indicated here, that comes down to one of the triangular equations. So that's, in brief, is why you get a coalgebra structure. But yeah, this is terribly abstract. I want to give a little bit more visual or geometric intuition about what these acyclic structures are really. I mean, how do we really think about them? A little lemma here. We don't have to spend too much time on it, but if you have a p-coalgebra structure, then remember that's the extra degeneracy that we had. And those extra degeneracies would kind of map back into the leftward direction. They actually do provide a splitting, which exhibits the fact that the map to the augmentation component is a co-equalizer of the maps coming before. For that reason, I mean, if you're looking at the co-equalizer of the source and target maps, then the co-equalizer should be the space for this object of path components, and therefore I'm writing this equation here. The augmentation component equals the object of path components, being the co-equalizer. And I give a quick demonstration here. So you're looking for these split co-equalizer equations. There are 2 of them which yield identity maps, but those come from co-unit equations. And up here, there's another equation for a split co-equalizer, but that comes out of a naturality condition for H. The idea is that the decalage will kind of push D1, you interpret that as being D2 pushed 1 over between the components 1 dimension up. It just kind of comes out. Yeah, as I say, I mean, we human beings, it's hard for us, I think, to understand comonads and coalgebras. So somehow, I don't know, the way I look at it is that we human beings, induction and recursion are more built into our brains than is co-recursion and co-induction. So, I mean, they're hard to understand the monads and their algebras.
Subsets are easier than quotients.
Yeah, that's right. That's another illustration of something similar. But in this situation right here, it's usually not so bad. If your underlying category E is complete and co-complete, then you have the option of looking at con extensions. So, I mean, what we have here, this decalage functor P is given by precomposition. A left con extension would be the left adjoint to this precomposition functor. And the right con extension would be the right adjoint to that. If E is co-complete and complete, then you would have both. And in particular, I want to focus on the left con extension and quote a famous result due to Eilenberg and Moore. This is the original paper where they define the category of algebras attached to a monad. You may have seen this result before if you've been studying topos theory. Then there's a result that says that, let's see, the category of pre-sheaves inside of a topos is also a topos. Eventually you come down to making a statement about a left exact comonad. But the point is that the free-sheaf construction is actually the monad that you use to construct a category of. Yeah, so this gives us a way out, is what it comes down to. That we have, in the case where E is nice, instead of thinking about the comonad P, we can think about the left adjoint, which will be actually a monad, and what that looks like.
Right.
Just hang on to your hats or strap yourselves in. I'm going to go through and actually calculate for you what this left adjoint would look like. It's going to be a little exercise in Monoidal lemma and so forth. So we're going to calculate the left adjoint to decalage. So let's start up at the top. We think that decalage is going to be a right adjoint. So we're looking at morphisms from x into decalage of, P, of y. And yeah, so we're looking at a natural transformation then. I should have said that let's take E to be the category of sets. Let's take E to be the category of sets. So a map here is a natural transformation. A natural transformation by the Monoidal lemma is y of d of n by the Monoidal lemma is given by the set of natural transformations from this representable into y. The set of natural transformations here can be identified with an end. You can manipulate this and say that maps into the end are in one-to-one correspondence with maps which are natural in n, but dinatural in m. Now you can use the times hom adjunction to swing this hom set back over here by a well-known adjunction. This time, however, you're going to get a family of maps which is natural in m, but dinatural in n. Maps out of here would be in one-to-one correspondence with maps out of the coend, and now we're back to natural transformations into y. So if we follow it all the way down, we can describe the coend formula for the left adjoint. Okay, so let's try to, again, I want to bring us back to geometry if we can. So I want to understand what this left adjoint is doing to a simplicial set X. Let's recall how geometric realization is defined. It's defined by means of a coend. Right. Thinking of geometric realization, that is a left adjoint to the singularization functor, which I'll get to over here. That makes that a co-continuous functor out of simplicial sets. Co-continuous functors out of a presheaf category, the presheaf category is a free co-completion. And so this will be determined by its effect on representables. And the effect of representables, the realization of this representable here is exactly in simplex. That is how we define geometric realization.
Right.
Well, what is this? I mean, if, for example, n were equal to 2, this would be a triangle. That triangle would be obtained by taking a cone construction on an ordinary interval. So what we do is you take, say, an ordinary line segment like this, line segment cross I, that makes a square. This push out would take one end of the square and squash it down to a point, and you would actually get a triangle. So this triangle would be exhibited as a push out of this type. And now we're just going to play a little game here. When I go back to the geometric realization that involves taking a, what's it called, a tensor with a bunch, take a coproduct of a bunch of copies. That's xn copies here. That will preserve this push out, and so we'll take in coends, and what we come down to is the fact that this push out is preserved. This, according to the coend description, is the realization of C of x, which we're trying to understand. This comes out, therefore, as being the outcome of a push out, which now turns out to look like this. So what we're doing is we're taking the geometric realization, we're crossing it with I over here. This object over here is gotten by taking the coend of xn, but that is simply the co-limit as a functor from delta op into sets. That co-limit will be exactly the augmentation component, and therefore what we're getting is a situation like this. And what's happening here, so imagine here's Rx, and I'm going to display Rx and imagine it has several path components. So imagine that this is Rx. We're taking Rx and we're crossing it with a unit interval. Okay, and then what we're doing, according to this push out, is we're squashing the t equals 0 end down to a point, and you're going to get a cone, therefore. We're going to get a cone on this geometric realization. But rather a cone, you're taking a coproduct of cones, one for each connected component, or one for each path component. So that's what this is, very concretely. You take the geometric realization, sum up all the cones of its path connected components, and that geometrically describes what this left adjoint is. Look at that picture over here. Just squash one end down to a point. So, let's summarize then. We described an acyclic structure as being a p-coalgebra map. According to the Eilenberg-Mohr theorem, that is tantamount to a C-algebra structure, which is easier to describe. It's the monoidal. The geometric realization of the C-algebra structure would now take this form. So remember that RC of x fit into a push-out from the preceding slide. RC of x was a push-out of the square that we had. So a map from the push-out into Rx is going to be exactly the commutative square. And so we have a commutative diagram here. That is the realization of the algebra structure. And we just kind of sum everything up now. What is this? What this is of course, a homotopy. This is an ordinary topological homotopy. What this map does, it chooses for each path component, it'll give you, for each path component, it will choose an appropriate base point that belongs to that path component. This diagram commutes, so you're saying that at time t equals 0, basically you're taking each path component and you're collapsing it down to that chosen point. At the t equals 1 end, according to the unit condition for the algebra map, you're going to get the identity. So you're getting a homotopy which contracts, taking you from the identity, mapping it down to the collapsing map to the chosen base points. This is a contracting homotopy in that sense. So that is the reason why p-coalgebras, thought of in terms of geometric realization, amount to exactly acyclic structures. What does acyclic mean? It means, well, maybe pi 0 is not trivial. Maybe it's not a single point, but all the higher homotopy groups are trivial. And finally, I'm going to state now, really at the end, I think I'm okay on time. I think I'm coming under an hour and a half, actually. But the universal property bar constructions, I don't know who to attribute this to. I've never quite seen it in this form. But it says that, okay, so it basically says that the bar construction is a universal acyclic T algebra. So here's the setup. You give it a monad T on a category, and suppose that you're given a simplicial T algebra. That's what I'm calling Y here. Suppose you're giving a simplicial T algebra Y, which is endowed with some acyclic structure, which is indicated by this p-coalgebra structure here. The idea is that for any map between the augmentation components that you start with, you can use that map to generate a map between the T algebra objects phi so that when you apply the underlying functor, you get something which is compatible with the P coalgebra structures. So that's the universal property. So there exists exactly one extension phi which has these properties. Morphism of simplicial T algebras and a morphism of P coalgebras.
So it's the universal simplicial T algebra with an acyclic structure that doesn't necessarily respect the T algebra structure.
Correct. That's vital. I mean, you remember, so we talked about the P coalgebra structure on the bar construction. That unit map that you start with, that's never a map of algebras. The unit map is never a map of algebras. It's like you're going from embedding a set into a free group or something. That's not a morphism of group. So it's absolutely, yeah, the P coalgebra structures operate completely independently of the T algebra structures. You have them kind of...
And that's actually what makes them useful, because you can have a contractible
That's right.
total space without having it trivial in terms of its group action.
That's right. That's right.
Sorry, that these two different structures and they interact. Can you build special sequences with that? Is that how they do it?
I don't know how to respond to that. I'll be taking notes about some of your questions and see if I can make some sort of intelligent response later, sometime later in the future. Yeah, no, thanks for asking, though. Very brief indication of the proof. I mean, if you've ever worked in homological algebra and you worked with these sorts of free or projective resolutions, the proof kind of follows along similar lines. It's a very simple inductive proof. So you start off with phi at 0. That's the map between the augmentation components that you're starting with. And you want to build up phi of 1 between the degree 1 components, phi of 2, etc. And the way it works is very simple. So you assume given phi of n, you apply the underlying functor here and follow it up with the P coalgebra structure at this level. So that gives you a map from UK into A, and just by basic adjunctions or freeness, it will be a unique algebra map phi of n plus 1, which will fill in this diagram, and that kind of bootstraps you off the ladder. And you simply, one has to check then that this is compatible with the P coalgebra structures and the faces and degeneracies. But it is. And that's the unique map, and that's basically how the proof works. And that's what I had to say today.